Alrighty, almost there. You're tired, how about me? You know how much I run around in this hour? Okay, so axial, that's a very ugly. Axial torque diagrams. T of x. We need T of x because that's what we need up there. You see that? Very important ingredient, how we get T of x. If you learned how to do n of x, you know how to do T of x. We did last time the special case in which you had just concentrated torques. So let's say that I have 10, units. Torques, oh no, we put the units there. Newton times meters. 10 Newton meter. And maybe here I have, I don't know, 3 Newton meters at this spot here. And say that here, in the middle of this, I have 5 Newton meters. I want T of x for this. We already did this last time. You go down at the end of the shaft. You go down where the loads are applied. You go down where the torques are applied. And you start building your T of x diagram by putting the shaft in equilibrium. Equilibrium in torsion means that what you need to do is sum of the moment x equal to 0. This is the first thing you need to remember. And the second thing that you need to remember is that positive torques, positive T, come out. When you cut, the torque comes out. A positive torque, wherever you cut, comes out of the section. Okay? So how do I build this diagram? I cut here, and if I cut here, I get only the torque at the end.
It doesn't matter which way x is going?
To find T of x, it doesn't really matter, but the way I drew it is this way, right? That's my x. Okay, so I cut here. I only see 10 Newton per meter here. And out of this comes my T of x. I do sum of the moment x equal to 0. I get minus T of x plus 10 Newton meters. And I get that my T of x in this region is 10 Newton meter. Right? So up here, I start walking up by 10. I get here, I'm at 10. I do the same here by cutting here. I'm not even going to draw it because I don't want to offend you. If I cut here, I'm going to have 10 going this way, 3 coming this way, the torque coming out. I'm going to get 10 minus 3. I'm going to go down to 7. I'm going to go down to 7 up to when something happens here. So this whole region is going to be 7 Newton meters. This is 10 Newton meters. And here, if I cut any place behind this phi, I'm going to see 10 plus 5 minus 3, 12. I'm going to have 12 here. 12 Newton meters. Okay, so you build the diagram for concentrated load just the same as you were doing for distributed loads. Sorry, I'm tired. You build the diagram for concentrated torques just the way you were doing for concentrated forces in axial loading. Okay? I was thinking ahead. I was thinking ahead because the next thing is that what happens if you have distributed loading? So the same way as in axial loading, I could have a force per unit length. Now I can have a torque per unit length. Say that I take this shaft here and say that the shaft has a length L, a total length L. And then from the middle of the shaft, so at L over 2, I go and I start twisting everywhere, just with twist distributed over the whole length. So it would look like this. I'm twisting everywhere. I'm like putting a torque which is distributed. A torque per unit length. Okay? So distributed torque is called Tx of x. And it is torque per unit length. And of course, the units are Newton times meter per meter. So the units, funny enough, come out in Newton. Isn't that funny? Not really, but it is. OK. Now, notice this little x that's there. Remember, our fx was positive if it was pointing with x. Boom, boom. I already see you with your right hand ready. My Tx is positive with the right hand rule. Right hand rule positive with x. So it's positive if it goes that way. So just to make our life easy, let's draw what is, so instead of having it drawn like that, on top of it, if I wanted, I could have instead done this thing. Double arrow distributed in the direction in which the torque is going. You see, this thing is the same as saying I have little torques per unit length distributed over this whole thing, and I absolutely advise you to always change this direction with the fingers to the direction with the thumb. Because here you can see directly that if this is my x-axis, my torque of x is positive. Let's say that my torque of x is equal to a constant for x greater than L over 2. And say that this constant is T0. And now let's say that is 0 on this end. OK, so the first thing that you do is you plot your Tx of x. The same way as you were first plotting fx of x. So if I do a plot, it means it's nothing here. And then here jumps to T0. This is your plot of your torque.
So this is T, not, it still isn't the, this lowercase t needs to the left. What is?
The lowercase t is the distributed load. The uppercase t is what's inside the shaft. The lowercase t is what I'm applying to the shaft, is what the world from the outside is doing to the shaft. OK? T is what's inside the shaft, what's carried by the stress, what controls the deformation, what gives you the strain. This one is what I'm doing to the shaft. And then from this, I obtain what the shaft feels by doing the same thing I was doing here. I do free body diagram, and I do sum of the moments equals 0. So in that case, for instance, if I want to find T of x, I cut here, zip, 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 zip. I cut at x. And if I cut there, I get, on this thing, I have T0 on top. Out of this comes T of x. I do sum of the moment x equals 0. I get minus Tx plus the integral from x to L of T0 in dx. Because T0 is a torque per unit length. When I want to sum it in the moment, I need to integrate over the length, the same way as I integrate fx over the length. So this one means that on this region is equal to T0 L minus x. This is the torque. This is the torque on this side all the way. If I cut any place from 0 to L over 2, my torque is going to look like that. It's going to reach T0 L over 2 over here. And then if I cut to the left of L over 2, then I have T0 only on the right half of the shaft. So when I find T of x, So this one here is for, this whole thing is for x greater than L over 2. If I'm at x less than L over 2, then I get minus t of x plus the integral only from L over 2 to L of t0 in the x. Because t0 only acts from L over 2 to L. There is nothing here. And so out of that, I get that this is equal to t0, L over 2, constant. So my torque of x will look like that. Okay? This is what the shaft feels. This is the torque of x that goes into there, and you need to solve your problems. Notice that the same way as F points the way to axial force, T points the way. So if T is constant, it means you're going to have a positive slope coming up when you walk the bar from this end. If torque is 0, means no change, right? So go back to this thing. We're going to do more problems on Monday, on recitation. We're going to do maybe some problem on Tuesday in class. We're going to go over more things. I'm going to assign you homework. Sometimes this afternoon is going to be on stellar. And you're ready to do your torsion problems. Okay? It was a tough class, and I'm glad that you're still alive.